the center to center spacing of what of our reinforcement. So then for our area of steel reinforcement required, which is the 666.59 millimeters, we are moving ahead to provide 16 mm diameter bars at 250 millimeters center to center, and this gives us a total area of reinforcement of what 804 millimeters squared. So whereas our section is requiring an area of 666.59 millimeters squared, we are providing 804 millimeters squared of reinforcement, which translates to 16 mm bars being spaced out 250 mm center to center. Now, having finished with determining the area of reinforcement for our section, we'll therefore move ahead and determine how to distribute our reinforcement within the base of our pad foundation. Now, the Bscode stipulates that if I have my LC, which is the distance from the face of my column to the edge of the pad, being less than or equals to 3 times my column dimension divided by 4 plus 9 times my effective depth divided by 4, then it means that my area of reinforcement that I calculated for can be spread equitably at the base of my pad foundation, or can be spread equitably along the full length of the pad foundation. So now we'll now move on and calculate for the value of our 3C over 4 plus 9D over 4. Our 3C over 4 plus 9D over 4 is given as 3 multiplied by 350 over 4, where the 350 is the dimension of our column, plus 9 multiplied by 150 over 4, where the 150 is the dimension of, or the effective depth of our pad foundation. Now, calculating it gives us a value of 262.5 plus 337.5. Adding the 262.5 to the 337.5 gives us a value of 300 for our 3C over 4 plus 9D over 4. Now, from our diagram that we looked at, or from our pad foundation, the distance from the face of our pad foundation to the edge of our pad foundation was 425 millimeters. So then comparing that distance, which is our LC, to the value of our 3C over 4 plus 9D over 4, we'd realize that our LC falls below the 3C over 4 plus 9D over 4, in which case our reinforcement can be distributed uniformly throughout the base of our pad foundation. Now, having finished with the design of our section for moment, we now move ahead and look at the design of our section for shear. As was said during the design of our floor slab, if you have a plate-like element which is very, very thin, the plate-like element first fills in flexure before it fills in shear. So before the loads would increase to a point that would cause it to fill in shear, the element would have already filled in what? In flexure. That is how come when we came to our slab design and our staircase design, we didn't check our slab and our staircases against what? Shear. Because we had our values being very, very thin or very, very small. And as has been stipulated by the Bscode, anytime you have a slab value which is lower than 200 millimeters, the element can be designed without checking for shear in that element. Because it is assumed that for such a very, very thin element, the element would first fill in flexure before it fills in shear. But then if we take the pad foundation that we are designing for, our pad foundation has a depth or has an overall depth of 200 millimeters, meaning that our pad is susceptible to what? Fill in shear. Now, once our pad foundation is susceptible to fill in shear, it means that we are supposed to go and check the extent of shear that would occur in the element and know whether or not we would have to provide for what? Shear reinforcement or not. Now, in designing for shear, the shear force value is usually calculated at a distance of D from the face of the column. And for our design, because our D value is equal to 150, our shear force value would be calculated at a distance of 150 from the face of that column. So then we are going to make use of the load from that 150 point all the way to the tip or to the edge of our column, to the edge of our pad foundation, to determine the amount of shear that would occur in our section. Our shear force value is given by multiplying our ultimate design pressure value to the area over which that pressure is being exerted, and that area is what has been shaded out on our column plan for us. So then our shear force value is going to be equals to 207.72, which was our ultimate design pressure as we saw when we were doing our load analysis, multiplied by the area of the shaded region, which is equals to 0.275 by 1.20. This gives us a shear force value of 68.54 kilonewtons. Now, having gotten our shear force value, we now convert our shear force value into a shear stress value. Now, this is arrived at by dividing our shear force value by the breadth and the depth of our pad foundation. We had our shear force value being equals to 68.54 kilonewtons. Now, in converting it from kilonewtons to newtons, we multiply the 68.54 by 10 to the power 3. And for the breadth of our pad foundation, as we saw before, it was equals to 1200, and our effective depth has a value of 150. This gives us a shear stress value of 0.380 newtons per millimeter squared. Now, having arrived at the shear stress value, we'll compare the shear stress value to the ultimate shear values that has been stated in the Bscode. Now, from the Bscode, our shear stress value should not be greater than either 0.8 root of our FCU or 5 newtons per millimeter squared, whichever is the lesser. Now, calculating for 0.8 of our FCU, we are going to have 0.8 root of our FCU, which is 35. This gives a value of 4.732 newtons per millimeter squared. Now, because we have our 0.8 FCU value being lower than our 5 newtons per millimeter squared, our 0.8 FCU value now becomes our limiting value, in which case our shear stress value should not exceed 4.732 newtons per millimeter squared. And as evidence, our shear stress value is 0.380 newtons per millimeter squared, which is far below our limiting value, in which case we can say that our compression shear is okay, or our section wouldn't feel under compressing what shear. So that we now move ahead and calculate for our shear capacity for our pad foundation. The shear capacity for our pad foundation, as we saw in our slab design, is given by the formula that is being stated or that is being showed on our screen. Now, substituting our values into the formula would give us a shear capacity of 0.690 newtons per millimeter squared. Now, having arrived at this shear capacity value, we'll now move back to the Bscode and see whatever provision or what provisions are made in the Bscode for the design of shear when it comes to slab elements. So then we take a glean through our Bscode, and this is a table that that is used for the design of shear reinforcement in slabs. From the first side of the table, it says that if our value for the shear force, or if our shear stress value is less than our VC value, then it means that no shear reinforcement is required, and therefore the area of shear reinforcement to be provided is being stated as what? None. Now, comparing our shear values that we came out with, we had a shear stress value of 0.380 newtons per millimeter squared, whereas our shear capacity has a value of 0.690. Comparing our shear stress value and our shear capacity value, we would realize that our shear stress value is far below our shear capacity value, in which case we are going to make use of the provision on the first row when we look at our shear stress table, which states that if our V value is less than our VC value, then it means that no form of reinforcement is required in our section, and the area of shear reinforcement to be provided is given as what? As none. Now, this moves on, or this tells us that when it comes to our pad design, we are not supposed to provide what? Shear reinforcement per the levels of shear that we are going to get within our section. So then, having finished with our vertical shear, we now move on to look at our punching shear, or the probability of our column punching through our pad foundation. Now, for our punching shear value, is usually calculated at a distance of 1.5 from the face of our pad foundation. The punching shear value is calculated at a distance of 1.5 D from the face of our column. Now, a distance of 1.5 D from the face of our column is equals to 225, since our D had a value of 150. So multiplying the 150 by 1.5 gives us a value of 225. So then our punching shear value is supposed to be calculated at a distance of 225 millimeters away from the face of the column. And when it comes to our puncturing shear value, it is not just calculated on one side of the pad foundation. It is calculated along or around the column. So then we measure a distance of 225 on all the sides of the column. Then the distance from that point to the edge of the beam would be used in calculating for the puncturing shear value of our pad. Our shear perimeter is going to be equal to 800 multiplied by 4, where 800 is going to be the dimension of our column, which is the 350, multiplied added to the shear distances from the face of the column on both sides of our column face. So to one side of our column face, the distance 1.5d is equal to 225. If we move to the other side of our column face, we are going to have the same 225 to the other side, in which case the total dimension of our shear perimeter, or our total shear perimeter, would be equal to 800 multiplied by both sides. Now, taking this as the pad foundation with this as our column, our shear or our puncturing shear is supposed to be at a distance of 1.5 from the face of our column, and that is supposed to be calculated along all the sides of our column. Now, the distance 1.5d, as we realize, is equal to 225 millimeters, with our pad or with our column having a dimension of 350. So then if we come to the other side of our column, it would also have another dimension of what? 225. Now, adding the 225 to the 350 to the other 225 gives us a total dimension of 800. So then, calculating our shear perimeter, which will be the perimeter along all the sides of our column, would be equal to the 800 on all the faces, and that gives us the 800 multiplied by 4, which is equal to the 3,200 millimeters. Now, having found our shear perimeter, we now move ahead to calculate for our punching shear force, which is equal to our stress or our ultimate design pressure multiplied by the area of our puncturing shear. And the area of our puncturing shear is the distance from our perimeter of our puncturing shear to the edge of our pad foundation. And that is what has been hatched out for us. So then this becomes our puncturing shear area. Thus, in determining the shear force value, we pick the pressure being exerted on the shaded area and we multiply it by that area. Now, for us to get the value of that area, we first find the area of the total pad foundation, which is given by 1.2 by 1.2. Then we subtract the area of, which is given as 800 by 800. To find the area over which our shear stress is going to be acting, we first find the area of the whole pad foundation, which is going to be 1.2 by 1.2, since our pad had a dimension of 1,200 millimeters. Then we come and subtract the area of our shear perimeter from that total area of our pad foundation. So then we'll have 1.2 multiplied by 1.2 less the 800 multiplied by 800, which gives us the 1.2 squared minus 0.8 squared, being multiplied to our ultimate design pressure of our pad. Now, this gives us a shear value of 166.176 newtons per millimeter squared. Having arrived at this value, would have to convert this value into a stress, and the stress is arrived at by, now having arrived at our puncturing shear force value, would have to convert our puncturing shear force value into a puncturing shear stress. Our puncturing shear stress is arrived at by dividing our puncturing shear force value by the breadth and the depth of our section, in which case the breadth of our section for our puncturing shear design becomes our shear parameter or our puncturing shear parameter. So then our puncturing shear stress becomes 166.176 multiplied by 10 to the power 3 divided by our breadth, which is our shear parameter, which was equals to 3200 multiplied by our effective depth, which is 150. This gives us a puncturing shear value of 0.348 newtons per millimeter squared. So once again, we compare this puncturing shear value to our ultimate shear stress value, which was given as 4.732 newtons per millimeter squared. And we realize that our puncturing shear value falls short of that value, in which case for compressive shear, our pad foundation is adequate against it. Then again, we'll compare this value also to our shear capacity, which we realized from the previous screen as being equal to 0.690 newtons per millimeter squared. So the one we have our puncturing shear value being less than our shear capacity. It means that from the table we looked at before, we are not supposed to provide any form of shear reinforcement within our pad foundation. So then, as has been stated, since our V value, which is equal to 0.348, is less than our VC, which is equal to 0.690, no shear force is required in our section. Now, having finished with that one, we move ahead and go for crack within our pad foundation. And for our crack check, we'll make use of the same provisions that we made use of whilst we were doing our slab design and our staircase design. And for the first part of that provision, it says that in no case should the clear spacing between the bars exceed the lesser of 3 times the effective depth or 750 mm, whichever is the lesser. And where we are making use of steel grade of 250 newtons per millimeter squared and our slab depth does not exceed 250 mm, no other shear check or no further shear check is required apart from the spacing. So then we move ahead and we look at our crack check. In doing our crack check, we'll make use of the same provision that was made use of whilst we're doing our slab and our staircase design. And the provision said in no case should the clear spacing between bars exceed the lesser of 3 times the effective depth or 700 millimeters. And moving forward, no further check is required on bar spacing if either grade 250 steel is used and the slab depth does not exceed 250 millimeters. For our design, we are making use of steel grade of 250 newtons per millimeter squared, and the total depth of our section is equal to 200 millimeters, in which case we are not exceeding the 250 as stipulated by our second condition. Now, once we are not exceeding this second condition, it means that after checking for our spacing, no other check ought to be made for our crack limits. So then we move ahead and look at our crack limits. For our crack limits, now our clear spacing is given as the center to center spacing less our bar diameter. And from our design of moment reinforcement, we realize that our center to center spacing was equal to 250 millimeters. Lessen our bar diameter, which is equal to 60 millimeters, gives us a clear spacing of 234 millimeters. Now, multiplying our D effective by 3 gives us 3 multiplied by 150 with an ultimate value of 45 millimeters. Comparing the two values, we would realize that our clear spacing, which is 23 mm, is less than 3 times our effective depth, which is 450 mm, in which case our crack check can be said to be okay. Now, having finished with our crack check, we now move ahead and provide the detailings of our reinforcement in our pad foundation. And a typical example is what has been shown on the screen, with the detailing being provided in plan and in section. And because we're dealing with a total of 1,200 mm, we had our reinforcement being spaced within a distance of 250 mm in both directions, since we're also dealing with a pad which is square in nature. Whatever reinforcement area we came out with for one direction was applied to the other direction. Now, assuming that we're dealing with a pad that was rectangular in section, then it means that the area of reinforcement for both planes, be it i.e. the X and the Y plane, would have had to be calculated for separately and provided for whilst we're doing the design for our moment reinforcement. Now, with this being done, we can now bring our curtains down on the design of our pad foundation, which also brings us to the end of our 5th unit. Thank you very much.